Hello, welcome back. Let's do another LeetCode problems today. Today's problem is 2685. Count the number of complete components. We are given an undirected graph with n vertices numbered from 0 to n-1. We are also given a 2D integer array for all the edges. Each inner array denotes an undirected edge between two nodes A and B. Our job is to return the number of complete connected components of the graph. As noted in the question, a complete connected component is a subgraph in which there is an edge between every pair of its vertices. First, let's talk about complete components. If we are given a complete component with n vertices, how many edges are there in the graph? If there's one vertex, no edge is needed. If there are 3 vertices, we need 3 edges to make a complete connected component. And if we have 5 vertices and we need an edge for every node to connect with every other node, there are a total of 10 edges needed. So we need n times n-1 over 2 edges. Each vertex in the graph will have n-1 edges. Now let's go back to the problem. Here in example 1, we have 3 complete components. So as you can see, there is n-1 edges for each of the vertex in each of the components. Now this question, we don't really need union find. There are probably other better ways of doing this, but I will show how I use union find to solve this problem. The approach is to use union find to identify all the separate components in this graph. And then for each component, I will scan through all the vertices and see if everyone has the right number of edges. Now, this question highlights the fact that the union find structure does not preserve all the properties of a graph. Hence, we would need 2 data structures. One data structure is to hold the groups of different components from union find, and the other data structure would be where we store all the nodes and all the edges of the graph. Okay, let's jump into the code. This C# code is provided in the GitHub links below. Again, we are using union find here. We have the find parents function, and we have the union function, and we also have a parent array for the union find. If you are new to union find, I would strongly recommend that you watch the first video of this series before continue with this one. I have the links to that video in the description below. For this problem, we are using several data structures. First, we have the parent array for the union find. The second data structure is a hash map for the adjacency list, where the keys are all the vertices of the graph. And the values for each key are where we store the vertices that share an edge with that vertex. For example, for vertex 0, the values are 1 and 2 because both vertex 1 and 2 share an edge with 0. I also have another hash map called groups where I store the information of each component. The key is the parent node and the value is the list of nodes that are in that component. So first, I will use a for loop to iterate through all the vertices in the graph. And then I will assign the parent of each node to be itself. This is the normal way we start building the union find structure. In this for loop, I will also initiate a new list for every node in the graph for the adjacency list. Next, using a for each loop, I will iterate through all the edges. Because each edge is an undirected edge, for each edge, there will be 2 entries in the adjacency list. For example, for the first edge 0, 1, we'll put 0 and 1 here, and then also 1 and then 0 here. In the for each loop, I will also perform a union operation to build up the union find structure. Upon the completion of the for each loop, the parent array would have these values. And the completed adjacency list looks like this. Next, I will find the group of vertices from all the separate components using the parent array. I use a for loop to loop through each vertex, and for each vertex, I will recursively find the parent, and then the parent will be used as a key. and then I will add the vertex belonging to that parent in the hash map. After this for loop is done, the group's hash map would have these values. Next, I will use a for each loop to loop through each group in groups and ask for each set of vertices whether they constitute a complete component. For example, in the first group, we have 0, 1, 2. There's a total of 3 vertices. For each vertex for a complete component, we should expect that each vertex should have n-1, so each vertex should have 2 edges. We go through each of the vertex, and we check against the adjacency list. And that is what the isComplete function does. Let's take a look at the first group. We have 0, 1, 2. For 0, when we check against the adjacency list, we see that there are 2 edges. For 1, we also see that there are 2 edges. For 2, the same thing. So this one is a complete component. I increment this com count by 1. And at the end, I return the number of complete components found. Okay, let's check if this works. And it looks good. As in the other video, I also included the solution using the weighted version of UN5. The code is here and is also provided in the GitHub links below. The difference is very small compared to the previous version. I only included the rank array and I modified the union function. I have a longer discussion about using the weighted variant of UN5 and the difference between the weighted and the quick version in the first video of this series. The link to that video is in the description below. Please take a look. Okay, now we check whether this version also works. And it looks good. And we are done for today. Hope that was helpful and see you next time.